Good day and good afternoon, everybody. So today we are continuing with our class in engineers petrology, and for this week we will, or at the end of these 2 or 3 hour classes, we will be done with our part of in engineers petrology, and then we will have next week and the following week we will talk about more in detail about metamorphic petrology, and by the mid of October we will be done with our class. So for training yourself, you should also answer all these questions here in these PowerPoints. So we finished last week with this figure. That this figure was an exercise, and there you have 3 questions regarding this figure, and today we will just continue with our class, and we are starting now with this figure here. So here we have another temperature versus pressure diagram. On the x-axis here we have the pressure in gigapascal. On the y-axis we have the temperature in degrees Celsius. So, and we are having here at temperatures higher than 1700 degree or even higher than 1900 degree, depending on the pressure. We have here the liquid, that is the Lersolite liquidus. We are sitting here in the Earth's mantle. I mean, if we are talking about pressure of 6 or 8 gigapascal, then we are talking about 60 or 80 kilobars, and then we are sitting already in a depth ranging between 180 to 240 kilometers. That means we are in the Earth's mantle. Below the liquidus, the Lersolite liquidus curve, we have melt and solid. That is a crystal mush. Here on that side, at lower pressures and temperatures ranging between about 11 and 1300 degrees Celsius, we have this dark colored field, and there we have the pressure and temperature condition where partial melting and magma generation takes place. Here we have now the Lersolite solidus, and here we have the upper mantle material rising along the ridge axis, that is about here. So where we are dealing with less pressures, so that means we are not that deep. So, and then we have here at this point, at this crossing point, we have the initiation of melt. So, and here we have then the geotherms here, that is the pressure temperature geotherm at the continent and old ocean basins. And here we have the geotherm in Archean shields. That means these are very thick and old shields. The thickness from the, and cool, they are cool, like the Kapwal. They are cool because they are that old, and then they had enough time to cool down, and they have a root, or they can have a root which is up to 400 kilometers thick. So what is written below, the diagram shows the solidus and the liquidus of the upper mantle. In the upper mantle we have Lersolites, and we have the adiabatic ascent path for mantle rock beneath the mid-ocean ridge, and the mid-ocean ridge, that is the MOR. And we have the geothermal gradients in an Archean shield, or in Archean shield areas, that is here. Then we have the stable continental platform areas, that is here, and the old, and that is far away from the ridge axis, oceanic basins. So what is additionally written here, in this model, the mid-ocean ridge adiabatic represents the path taken by parcel of mantle rock. So, and that is the asthenosphere that rises and crosses lersolite solidus at about 1.8 gigapascal. Yeah, that is 1.8 gigapascal that we have here. It is a melting initiation crossing point, at which point it begins to melt. It continues to melt all the way up to the base of the crust. The partially molten region is depicted as the gray area, and that is this gray area here. So going now to the next slide. Here we have another nice temperature pressure diagram. Here we have the solidus, yeah, and here we have certain curves. So, and below we have these two diagrams. Here we have the partial melting zone, that is this zone here where we are having or creating partial melt. And when we are creating partial melt, this melt will rise up, and at the top we will form new crustal material. Here we have the lithosphere, here we have the asthenosphere, and here we have the different geotherms, yeah, and there we have the different temperatures. Or we have number B, here we have the movement of lithosphere, and then we have below in the asthenosphere, lithosphere boundary, we have the emplacement of a plum, and then we have the rise up of a melt. So, and then we will make here or form here at the top, at the surface, probably a shield volcano. What is written below? Bottom left, partial melting and melt accumulation in passive melting regime beneath an extensional environment, such as a mid-ocean ridge. So yes, that is such as a mid-ocean ridge, you know, the middle ocean ridge basalt, where extension of two lithospheric plates causes the asthenosphere to passively rise to shallow depth and partially melt to generate the middle ocean ridge, or the basalt for the middle which you were forming at the middle ocean ridges. The magma generated within the triangular partial molten regime focuses to a form of new crust black at the ridge axis, while the melt depleted residue is transported laterally as shown by the arrows, yeah, to form the lithosphere. So here we are forming the lithosphere, and that is then our peridotites, yeah, and these are the residuums of this melt, yeah. We are forming here at the top, we're forming our gabbro or our basalt, and here we have the residuums, and this is then depending on the pressure, the dunite, or it is the lersolite or the harzburgite and so on, yeah. So, and that forms then our lithosphere, and the lithosphere or here below the new oceanic crust, this lithosphere consists of peridotites. Bottom right, partial melting in a plume or hot jet environment in which a hot plume rises from the deep and partially melts near the lithosphere asthenosphere boundary. That is then here, yeah, there we are making melt. Rises from the deep, blah blah blah. The melt collects and ascends via cracks through the lithosphere to erupt at the surface. In the present example, the lithosphere is moving from left to right, whereas the hot plume remains stationary. That is like we have the situation in a hotspot environment where we are forming then a volcanic chain, and the most the most prominent volcanic chain, hotspot chain. These are the Hawaiian Islands. So as it is written here, this arrangement results in the volcanic island chain like the Hawaiian Emperor chain in the Central Pacific, in which the volcanic islands get progressively older as they move away from the hotspot or plume. So then we have here the dashed lines that is in the top panel. So because we would like to know what F means, yeah, what is the F? We have here the solidus, and at the solidus we have an F which is 0. So top panel, so I mean these dashed contours, these are the isotherms, and at the top panel, paths of mantle parcels in the plume path B. That is, here we have the plume of path B, and that is the path B, and that is the path A, as it is shown here. F means melt fraction. So F of 0.01, that means we have a melt fraction of 1% and 99% solid matrix or residue. Each dashed contour represents a fixed value of F. So that means here we have already a melt fraction of 0.05, yeah? That means we have 95% solid material and 5% melt, and here we have 0.25. Yes, and then we have here 75%. We have solid material, and the melt fraction of this 75%, that is then 25%. Okay, you got it? Yes. Coming now to the next picture, here we have a subducting plate beneath another oceanic lithosphere. We have here the subducting plate, partial melting takes place, that is in like this diagram which I used for start today, that is at a relatively low pressure, not higher than 1.8 gigapascal, this 18 kilobars, yeah. And then you are sitting in a depth not deeper than 60 kilometers. Then we have here the mantle wedge, here we have the dipping slab, here the mantle wedge, and we have the rise up of the melt, yeah. So and then in the overriding plate we have the melt will extrude or intrude, yeah. If we have an intrusiva, we are forming a plutonic rock. If we have an extrusiva, then we are forming a volcanic rock, and we are forming a volcano as well. So with the subducting plate, the release of water takes place. This will decrease the melting point in the mantle wedge, and then our peridotite in the mantle wedge will partial melting will take place, and we have the rise up of melt. So, and here we have now on the right hand we have this temperature pressure diagram. We have here in the upper part the lithosphere, here we have the asthenosphere, and we have here the vapor-free solidus, yeah, and here we have the H2O saturated lersolite solidus, and that is the area where our melting will take place, yeah. These are the temperature and pressure conditions, and this melt will rise up and form then, for example, an extrusiva as seen on the figure on the left. So, what is written here? Hydrous melting in a subduction zone. Left. Schematic cross-section of a subducting plate where H2O rich fluid is given off the subducting plate. This fluid lowers the melting temperature of the mantle wedge, as I told you, above the subducting plate, triggering melting, right? This diagram illustrates the extent of which H2O lowers the mantle lherzolite solidus. It also shows the vertical temperature gradient in the wedge. So, and that is here seen at the arrow. Note that this path is lower than the volatile free solidus, therefore melting would not occur in the asthenosphere if H2O were not added to it. So here we have another nice triangle about a triple junction, and you know the triple junction, you can easily observe them when you are looking at the thin section. So, and then this triple junction melting starts then, yeah, here we have three minerals, and here we have the triple junction, and there melting can start. Here we have very low angles, less than 60 degree, and here we have bigger angles. So, and the relation of the angles is very important when we are talking about the pathway of fluid and melt, and also not only the pathway of fluid and melt, it is also very important in the melt generation. So we have here A, B, C, and what is written here, we are talking here about melt distribution in pore spaces between mineral grains in a rock. A, B, and C applied to mafic melts, and D to F applied to felsic melts, yeah? You know what a mafic melt is, you know by now what a felsic melt is. A mafic melt is a silica undersaturated melt, whereas a felsic melt is a silica saturated melt, yeah? Interfacial energies, differences between the two adjacent grains and between the melt and grain are given as gamma GG and gamma mg. Respectively. A. Mafic melt occupancy at a triple point junction in a peridotite due to small dihedral angles. Yeah, that is the situation here. B. Mafic melt channel in 3D along the grain boundaries between the three adjacent grains in a peridotite. That we have B. And C, we have a perspective diagram of B. Yeah? Here you have the whatever you want, the olivine or the orthopyroxene grains, and that they are how related. Here we have our triple junction. So, and that is how the melt will be formed in pore spaces in minerals, depending on it. If we are talking about a mafic rock, which is silica undersaturated, or a felsic rock, which is silica saturated. So then we are going to D. We have felsic melt occupancy at a triple point junction. That is then this one, yeah. And there we have here much bigger angles, yeah. E. 3D diagram showing the distribution of melt along the vertical dimension. So here we have not an interconnected network of melt like we have it here, yeah. So that means a mafic melt is much more mobile compared to a felsic melt, yeah. So, and why is this? Because in the in felsic melt, we have much more silica inside, and all the silica tetrahedrons, they are connected to each other, and therefore they have felsic melt has a higher viscosity compared to a mafic melt, and therefore a mafic melt is much more mobile compared to a felsic melt, yeah? E3D diagram showing the distribution of melt along the vertical dimension, and F gives us the perspective drawing of E. So, and therefore we have just such a single bubble inside. I think you got this by now. Coming now to the next diagram, we are talking here about progressive compaction of melt segregation. So here we have a solidified rock, yeah, with all the different minerals inside, and here we have some melt around, and we have here maybe 20% melt of this rock, and here we have already 40% molten of this rock, yeah. So what is written here? Left 3 panels show schematic drawings of how compaction proceeds. In the beginning, uncompacted, that we have here, uncompacted, the melts are located along the grain boundaries. Yeah? Therefore, we have these more thick grain boundaries, and there is the melt compacted. And if we are talking about a mafic rock, then this melt is along all the grain boundaries. With progressive compaction, the solid material settled to the bottom. Here we have solid material, yeah. Here we have then solid material. Here we have still melt along the grain boundary. And here at the upper part we have just melt. So, with progressive compaction, the solid matrix settles at the bottom, while the melt separates and collects at the top, yeah, because the melt has a lower density and then it is rising up to the top. The right panel shows relative velocities with which the melt, that is the velocity Wm, and the matrix Wo separates from another, yeah? So, and here we have then the rise up of melt. And that is the velocity of the melt compared to the matrix, yeah, because the matrix goes down, becomes solidified, and the melt rises up, yeah, and these are, we have here the relative velocities. The velocity signs represent the direction and along which material is flowing. Plus means for upward flow, yeah, that is the melt will flow upward like here, and the matrix goes downward. Whereas here the melt flows upward and the matrix goes downward. And minus for downward flow. The melt velocity is high in the lower part of the compaction column and becomes constant above a certain height. The matrix velocity is lower than the melt velocity at all heights. So compaction, here on the left hand we have compaction length as a function of grain size. So we have here now the compaction height in meter, 0 to 1200, and here we have 1200 meters, and here we have the porosity in our rock. And that A is the grain size. Here we have a grain size of 0.3 centimeter. here we have a grain size of 0.2 centimeter. So and along this curve we have then the melt fraction F. So if we have bigger grains, then we have a lower porosity, and then the melt fraction is also lower. So when we have a higher porosity, that means we have smaller grains because the surface is then bigger, then the melt fraction becomes then bigger. On the left hand, we have the phase relationship in the system: diopside, anorthite, forsterite at 4 different pressures. We have here 1 atmosphere, that is at the surface. We have here 1 gigapascal, that is 10 kilobars. 1.5 gigapascal is 15 kilobars. 2 gigapascal, then we have 20 kilobars. So and therefore we have then here we have our source peridotite. Yeah, it is plagioclase peridotite, and plagioclase peridotites are low pressure peridotites. I mean, that is then a lersolite. Yeah. So and then we have here the melt relationships. We have here A, B, C. So what is written here: phase relations in the system: diopside, anorthite, forsterite at 4 different pressures. Yeah, these are these pressures here. Points A, B, C, and D are invariant points that are of interest in our discussion in the text of partial melting of a peridotite source, as discussed in the text. Yeah. So I mean, when we have at 2 gigapascal, then we will start to melt at point A a more forsterite rich rock. And when we are melting at low pressures at the atmosphere, then we will partial melting will take place in a more diopside, anorthite rich rock, and that is just along these 3 points. These are then the curves where partial melting takes place at different pressures. And here we have the composition: diopside, diopside, anorthite, forsterite. Yeah. So the composition, here we have some composition pressure diagrams, and at the diagram at the top we have CaO on the y-axis, and the pressure on the x-axis. In the diagram in the middle we have MgO on the y-axis, the pressure on the x-axis. And on the diagram below we have SiO2 on the y-axis and the pressure on the x-axis. So, and here we have the composition of melts at the invariant point at 5.7, plotted here in terms of pressure versus oxide weight %. Yeah. So, and if you are looking at the diagrams before, we have here at the surface, at a pressure of 1 atmosphere, that is then at point D. Then we have here at point B, let us just check, not this one. This one we have here at 2 gigapascal A, B, C, D. So, and when we are when partial melting on the at lower pressures occur, then the partial melt is then more silica rich. So, and at lower temperature it has then less magnesium inside because there is less olivine formed, so but it is more rich in silica and in calcium, and that is due to the fact that we are melting here more anorthite, yeah, compared to forsterite. When we are going to higher pressures, then we have more forsterite in the system. So, and then our magnesium concentration rises then up as well. So now let us just continue. I think you got the point what I was telling. At lower pressure conditions, the partial melt which you are producing is more silica and calcium rich, whereas if you are going to higher pressure, it becomes more magnesium rich because you have more forsterite, that means olivine, in the system, yeah? So now we are going to our next slide. What we have here, we have an diagram for a certain number of rare earth elements. We have here light rare earth elements inside. We have heavy rare earth elements inside. So, and we have here the light rare earth elements, or the little earth elements. They are on the left hand of the diagram. And here we have then the heavy rare earth elements on the right on the diagram. And they are listed from left to the right regarding their incompatibility, but I'm sure you have already heard about it in your geochemistry class. So here we have numbers ranging between 10 and 0.0001. Here at numbers bigger than 1 or higher than 1, we are talking about compatible, and below we are talking about incompatible. So we have then different curves here. That means we have plotted here the ratios between mineral in liquid, and here we have it for a spinel. For the curve spinel and liquid, then that is the spinel and liquid, that is this one. Here it's very, very flat. Then we have for autopyroxene and liquid, that is this one here, yes. We have here it's all very incompatible. Then we have here Shitman. Then we have here amphibole liquid, that is this one, yeah. Then here we have the round thing, we have CPX and liquid, that is this one. All the elements are just incompatible. So here olivine and liquid, that is this one with the triangle here. So, and here we have the garnet and liquid. Here we have then the heavy rare earth elements. They are very compatible then in the garnet, yeah. And then we have here plagioclase and liquid, yeah. So if we have here, only in the garnet a compatibility for heavy rare earth elements, and indeed the heavy rare earth elements are very happy in the crystal lattice of garnet, yeah. And in all the other diagrams we have an incompatibility. So how you are doing this? You are measuring all these trace elements in the mineral and the regarding garnet, and then you are calculating the ratio, and then you know where they are more compatible. Are they more compatible in the mineral or in the liquid? Yeah. So what we have here the concentration of solid melt in solid in liquid in ppm, and versus F, that is the melt fraction shown for two different melting models. Yeah, so we have here a modal fraction and we have here a modal batch. So that is now not important for our class. The thing what you should know now as a third year student is always that you are starting to melt a certain rock, so and then you are leaving a solid bag, and a certain mole fraction or a certain fraction, which is always called F, will melt, and this melt will become removed from your solid rock. So, and then from your parental rock, or from your parental rock or parental melt, you are making two rock types out of it. You have the residual rock, which is living back, and this rock which is formed by the melt, which becomes removed from your system. So, and there there are different methods how to measure this. You can use the trace element, or you can make a solid liquid fraction diagrams where you can see how much percentage of your parental will be in the residual as a solid and how much will be removed as melt and become then also again a solid. What do we have here? We have here something olivine liquid equilibrium at 0.0001 gigapascal. That is 1 atmosphere, and that is at the Earth's surface. So we have here dashed lines are isotherms and temperatures are in degrees Celsius. Yeah. So, and here we have XFE in the liquid on the x-axis, and we have the XMG in the liquid on the y-axis. So, and that is just the FM exchange which you can observe in olivine. Yeah, you have the forsterite, the magnesium-rich and olivine end member, which is the forsterite, and you have the iron-rich olivine end member, which is the firelite. So, and then we have here at these lines, we have nearly a pure forsterite, FO95, FO90, FO85, FO80, FO75, and then we have here FO10. That means we have here a very iron-rich olivine inside, and a very iron-rich olivine. So, and here we have the temperature curves, 1200 degrees, 1300, 1400, 1500, going up to 2000. So, and here we have we are producing then a forsterite, which has a lot of, an olivine which is very rich in magnesium, and we have then also a high magnesium fraction in the liquid, like it is shown here at these lines. Yeah, here we have 0.5, 0.45. So, and here we are going then to lower temperatures where we have more iron in the liquid, and we are forming a more iron-rich olivine. Yeah. So here we have another a nice diagram on the left hand, how the eutectic point is moving in dependent on the pressure. Here we have 1 atmosphere, 1 gigapascal, 2 gigapascal. Here we have the eutectic point at 1 atmosphere for two minerals or phases A and B. When we are increasing the pressure, then our eutectic point will move here from more left side to the more right side. Yeah. So what is written here, isobaric phase diagrams for a hypothetical binary system at 3 different pressures. B, an isoplectic section do we have here, yes. For the bulk melt composition, M is constructed based on phase relations in the 3 isobaric diagrams in A. So here we have the eutectic point here at the atmosphere pressure, yes, so at 1 bar, that is here, at very low temperatures, yeah, here we have the pressure, here we have the temperature, so and here we have the L1, that is the liquid point here, and E1, that is the eutectic point here. Then we are moving up with the pressure. Then while we are moving up with the pressure, we are moving also up with the temperature. So, and here finally we are coming to eutectic point E3 at 2 gigapascal, where we are also moving up the temperature. So, and that is the calculated PD diagram for the melt M. So that means the melt relationships changing also always in the bulk with the different pressure and temperature conditions. That is what you should have now in mind. So here we have another bunch of triangle diagrams, also depending on the pressure. Here diagram A at 0.5 gigapascal, here at 1 gigapascal, here at 1.5 gigapascal, yeah? So, and here in dashed lines, we have the temperatures. So we have here 1300 degrees Celsius, 1200 degrees Celsius, 1000 degrees Celsius. Here we are forming a melt at a pressure of 0.5 gigapascal at 1200 degrees Celsius. In this diagram, in this ternary system with the 3 phases A, B, C. So, and here we are coming then to our eutectic point. So, and here the same for at 1 gigapascal, we are forming the melt here in this point at 1100, and here at 1.5 gigapascal, we are forming it here at 1.5 at 1400 degrees Celsius. So, and now you can see how the composition varies here in our ternary system using only on the pressure and temperature dependence. We are forming then a rock or a partial melt, depending always from which side we are looking at it, dependent on the pressure and the temperature conditions. So what is written here? Multisaturation in a hypothetical ternary system ABC, that is what I told you. Isobaric phase diagrams at 3 different pressures are shown in A, B, and C. So then we have liquid path of melt composition M, yeah? The liquid path of melt composition M is shown as dark line that point at these pressures, yeah? That is the liquid path. From this information, an isoplectal section for M is constructed in D. Note that M is multiple saturated at 1 gigapascal E. Isoplectal section for melt composition N. So that is then here the melt composition N. N is not multiple saturated at any pressure. So that here is the melt composition N, yeah? At a certain pressure and temperature. So and here we have then the melt pass with at a certain temperature and pressure, and here we are cooling it down along this path, and here we have this pressure temperature diagram. Here we have phase A plus B and liquid, A plus liquid, and here we have only liquid. So and here we have the solidus curve with the three phases A plus B plus C. That is always at these points, yeah, that is here. If you are if you are looking here, we are dealing here at 1.5 gigapascal, that is here. Then we are going there, we are coming then to a temperature close to 1200 degree, which is here. That is at the solidus curve. If we are crossing here the solidus curve, then we have here at higher pressures we have phase B and C and liquid, or even higher temperatures we have only phase B and liquid. So if we are going to lower temperatures, we have A and B and liquid at if we are going at lower pressures, we have here A and B and liquid, and we have here only A and liquid, and here we have just liquid. Yeah, that is the dependence, how it is related to the pressure and to the temperature relationship. So next diagram, here we have at the top a multi-phase saturation diagram at 1 gigapascal. Here we have clinopyroxene, olivine and silica. So we have here olivine and liquid, then we have orthopyroxene and liquid, and we have clinopyroxene and liquid. And here at this small dot we have a multi-phase saturation at 1 gigapascal. So we have here a saturation of Middle Ocean rich basalt with olivine, orthopyroxene and clinopyroxene. That was experimentally determined at 1 gigapascal. So 1 gigapascal means we have 10 kilobars and we are sitting in a depth of about 30 kilometers. So and this is this phase relationship, because when we are going to this side, we are going more and more to the silica saturation, and silica saturation, we do not deal with silica saturation in the Earth's mantle, or let us say in the peridotites, yeah? So and then it depends always in which direction we are going. Here when we have going more to this direction, then we have CPX plus liquid. If we are going to this direction, we have olivine plus liquid. If we are going more to this direction, we have orthopyroxene and liquid. And when we are cooling down, then we have here at this point the multi-phase saturation. So now we have the diagram below that we have here clinopyroxene, olivine and statite is the same triangle. Here we are going even to the more silica saturated side and forming then the feldspathoid. And in this system we are talking about the feldspathoid nepheline. Here we have again the pressure relationship, 1 atmosphere, then we have here 1 gigapascal, 1.5 gigapascal, 2 gigapascal, and that is the chemical composition of the Middle Ocean rich basalts. So in the Middle Ocean rich basalts, they are extrude at the Middle Ocean ridges, so we are going along this curve at 1 atmosphere. So in the peridotites, here they are going on along this curve and these are then our residuums, yeah? Here that is the melt fraction which becomes extracted, forming then the middle ocean ridge basalt, and here we have the regarding residuums, that these are then the peridotites. So what is written here, Stolper 1980 has constructed this diagram, and he or she has done experiments. So that means experimentally determined multiple saturated pseudo-invariant points in a natural basalt peridotite system at several pressures. He noted that middle ocean ridge basalts do not touch any of these points at any pressure, and therefore concluded that morbs are not primary magmas. Yeah? The morb, that is the melt fraction which becomes removed from a melt, and here we have then the residuums, yeah? And these residuums consist of clinopyroxene, enstatite, and olivine. So here we have another diagram, yeah, where they are using here the isotopes. Here we have 143 neodymium to 144 neodymium on the y-axis, and on the x-axis we have here the 87 strontium to 86 strontium ratio. And on the left hand we have here the 87 ratio to 86 ratio, and here we have the lead 206 to lead 204. So now we have to figure out, here we have the neodymium isotopic ratios and 87, 86 strontium ratios here for the Pacific Middle Ocean ridge. Here that we have the mantle trend, and the mantle trend is on the line, and here we have the Colau volcanobasalts from Hawaii. Yeah? So and now we are comparing DMM with PUM, and therefore we must know what means this POM with DMM. It's written below. Some isotopic ratios and rare earth elements pattern normalized to POM are shown for primitive upper mantle. So the primitive upper mantle is the POM, which is the major source component for oceanic island basalts like Hawaii, and the depleted morb mantle, that is the DMM. So when they are lying on one line, but they are both have their source from the upper mantle. So and now we are comparing them. For example, here we have the comparison between neodymium isotopes compared with strontium isotopes. They are lying here on the line of the mantle trend. So, but here the field for the Pacific morbs and the basalts from the Hawaiian island is different. So, and therefore we can use the isotopes for classify our different rock samples, and then we can get an idea or can construct a geodynamic model in which geotectonic settings this rock has found. So here, for example, we have here the strontium isotopes versus the lead isotopes. That is then this huge variation in Hawaiian basalts, which are again overlying with the primitive upper mantle basalts, with the primitive upper mantle. So, and here we have the Pacific morb, which is completely different and is also not overlying with the depleted morb mantle. The same we have here the helium isotopes plotted against the strontium isotopes. Here for the Hawaiian lavas. Here the primitive upper mantle goes here up. And here we have the field of the morphs. So and then on the other side, on the right side, on the right side here we have the strontium isotopes plotted versus the osmium isotopes. So and all these different isotopes can be used as a geochemical fingerprint to identify in which geotectonic setting our different basalts which we have sampled in the field are formed. So and here at the bottom we have then a PAM normalized raw earth elements diagram. Yeah, it has been normalized to the primitive upper mantle, and then you can see how the different basalts are varying. So here we have the curve for here we have again the trace elements from lanthan over europium to the lutetium light rare earth elements, going here to heavy rare earth elements. We have also some high field strength elements inside, yeah, like the samarium and blah blah blah. So and here we have this relationship for the Hawaiian tholite basalt. Then we have here it for the mean morph crust. Here of course we have here a straight line at the primitive upper mantle, because it is a primitive upper mantle normalized diagram. And here we have the depleted morph mantle that is shown here in this curve. Coming to our next figure, we have here the basalt tetrahedron, yeah. So we have here figure A, we have the diopside at the top, we have here the diopside at the top, here the nepheline, the olivine, the hyperstene, the quartz, and here the plagioclase. So on this hand we have then quartz tholites. These are quartz saturated basalts, yeah. We are calling this a quartz tholite. Then we have here the plan of the silica saturation. That is the plan of the silica saturation. So and here we have the critical plan of the silica undersaturation, and therefore we are forming here a rock consisting of hyperstene, diopside and plagioclase, yeah. So here we have then the olivine tholite, yeah. Olivine, hyperstene, diopside, plagioclase. And if you are going to that side, we have then the very silica undersaturated rocks, which consist of nepheline. We have nepheline, olivine, plagioclase, diopside. On this plane we have olivine, plagioclase, diopside. On this plane we have hyperstene, plagioclase, diopside. On this plane here we have diopside, hyperstene, quartz. So that is the basalt tetrahedron after Yoder and Tilly from 1962. So now we can flip this basalt tetrahedron in 3 triangles. We have here this triangle, nepheline, diopside, olivine. Nepheline, olivine, plagioclase. So what have I told you now? That is the nepheline, olivine, plagioclase. That is this triangle here. So here we have now the next triangle. That is the triangle here. Olivine, orthopyroxene, plagioclase. So and here we have the next one. Orthopyroxene, quartz, plagioclase. That is this triangle here, yeah. So and therefore we can use this relationship to classify our basalts, our typical composition of the basalts. So, and here we have, for example, the a trend starting here from a quartz tolite over olivine tolite, over basanites, and here to nephelinites, yeah? So that is here then the exploded view of the basalt tetrahedron showing where basaltic rocks plot, yeah? So, and that is shows then you the variation of different basalts depending if they are silica saturated or silica undersaturated, yeah? So, and that is then, for example, one can use this relationship very nicely when one is working like on a volcanic chain, you know, on a hotspot chain like the Hawaiian basalt, and then you can describe the chemical trend from your basalts. If it is going more from alkaline to tolliitic, or tolliitic to alkaline, or whatever you want. But that is then a thing for next semester when we are talking about the petrogenesis of the igneous rocks. So here we have the AFM diagram for igneous rocks. Do not change this with the AFM diagram for the metamorphic rocks. Here the AFM diagram for the igneous rocks, we have here F, that is iron 2 plus iron 3 plus. We have M for magnesium oxide, and we have A, which we are not using for aluminium like in the metamorphic systems. Here we are using A for sodium oxide plus potassium oxide. So, and here we have two curves inside. We have here the tolliitic trend, yeah, that is for the tolliites. And here we have the calc-alkaline trend. We are starting here with a high aluminobasalt, going over an andesite to an dacite, and finally to a very silica-rich, silica-saturated volcanic rock, which is then the rhyolite, and that is the alkaline trend. Yes, and we will then also discuss next semester where you can observe the alkaline trend. So here we have another nice diagram. We have here AB, these are two cooking pots. So in the dark material that is melt, and then we have some crystals inside, and these crystals are sinking down to the bottom of the melt. So that means we have here differentiation process. So, and when what means this? When we are crystallizing crystals from a melt and they are sinking to the bottom of the of our cooking pot, that means the crystals having a higher density compared to the surrounding melt, of course, then they will sink to the bottom of the cooking pot. And when we are looking at this in natural system, then we are looking at a magma chamber, and in a magma chamber crystallization take place, and the crystals which show a higher density compared to the surrounding belt will sink to the bottom of the chamber. So if they are floating up like in the cooking pot number B, that means the crystals which we are forming out of our melt having a lower density, and then they will just float up at the top of the magma chamber, which is shown then in diagram number C. We have the wall rocks at the bottom, and we have the wall rocks at the top, yeah? So, and then we have crystals which are sinking to the ground of the magma chamber, yeah? That these are then we are forming at first an olivine-rich layer like here, because olivine is a mineral which formed very early in the fractions in the crystallization sequence, because the olivine is formed at high temperatures. So it formed and very at the beginning having a higher density compared to the surrounding melt, sinking down to the bottom of the magma chamber, and here you will then form a chilled margin between the cold wall rock or the cooler wall rock and the crystals which are sinking down. So in the crystal chilled margin, there we are trying to or our rock melt mass will try to get in equilibrium with the surrounding wall rock. So, and that means it will come to the same temperature, and then it will stop with mineral reaction. So after when the olivine-rich layer is formed, we are forming the next layer, that is then a pyroxene-rich layer. So, and there we are forming pyroxene crystals. So then minerals which having a lower density will float up of the magma chamber, and there we have then a plagioclase-rich layer, because plagioclase has a lower density compared to the surrounding melt, will then float up. We have here also a granophyre, and we have between the wall rock and the crystals which are floating up, we have the next chilled margin there. So number D shows us now a diagram. The schematic variation in mode of chemical composition within a sill. So the olivine will sink down in this sill. Yeah, we are forming then at the bottom an olivine-rich layer. The CPX will sink down. We are forming then in this sill also a CPX-rich layer. The plagioclase will float up. We are forming here a plagioclase-rich layer at the bottom. When we are looking at the MgO concentration, then our bottom here is much more rich in magnesium oxide, because it is in the olivine and in the pyroxene, whereas at the top layer is more rich in aluminium oxide, because here we have then our plagioclase, and the plagioclase is hosting our aluminium. So, and here we have a panoramic view of the Palisade sill in New Jersey. So, and here we have this sill, yeah, and where you can go there when you are sometimes around in New Jersey. Then you just can go there, and then you will form here. There you will find at the bottom, you will find more olivine pyroxene rich rock, which are more enriched in magnesium, of course, because the olivine and the pyroxene, they are hosting the magnesium, whereas at the top you will find more plagioclase rich layer, which is then also more rich in aluminium. So now we are going to the lunar highland anorthosite that is on the moon, yeah? So in there we have a cross section, or this cake. It's just from core to the surface from the moon. We are forming here an anorthosite, and an anorthosite, you know, that is a rock which contains more than 90% of plagioclase, of anorthite plagioclase. And this layer was formed by the floating plagioclase crystals which are floating in the magma ocean up to the top, and the more olivine and pyroxene crystals which shows a higher density, they are sitting here at the depth. So, and then you are forming here your anorthosite layer at the top on the lunar highlands of the moon, and here at the depth of down to 350 kilometers, you have this more rich orthopyroxene and olivine rich layer. What is written here? Formation of the lunar highland anorthosite rock with more than 90% of plagioclase on the moon is thought to be to flotation of plagioclase crystals and settling of mafic minerals in a large magma ocean that covered the moon very early in its history. Here again a nice diagram which are showing us here at the top and at the bottom we have the chill margin. Then we have crystallization from roof inward, that is here, yes, in the magma chamber. Here we have the solidification fronts of both. Here in the middle we have melt, and here we have crystallization from bottom inward, yeah. So that is how it looks like in such a magma chamber, because we have here at this sketch, we have here a magma chamber. Here we have a vent where we have then maybe a continental flat basalt. Here we have our chamber, and in the chamber it cools down from outside to inside. That means we have here our residual melt inside the chamber, and here at the rim it becomes then more and more solid, and the crystallization takes place from rim to the core in our magma chamber. So what is written here, sketch showing passage of basalt melt through a system of silts and dikes prior to eruption. Here we have dikes, yeah, and here we have then silts. B, it is an expanded sketch of a sill to illustrate in situ crystallization of the sill magma from the roof and at the base as a result of heat loss due to the surrounding rocks. Yes, you have here this, you are cooling down from the top and from the bottom. Crystallization take place, yeah, here seen in this area and then in the dotted area. So, and the residual melt is then here inside in the core of your magma chamber. So here we have another nice diagram here, AB. On the left hand we have again a ternary system consisting of anorthite, forsterite and silica. We have here anorthite plus liquid here. We have here spinel plus liquid. Here we have forsterite plus liquid. Here in this field we have enstatite plus liquid, yeah. So, and from A over B, C, D, we have our cooling path. So, A, crystallization of a basalt magma is illustrated in the system forsterite, anorthite, silica. Liquidous phase boundaries at 1 atmosphere and 1 gigapascal pressure are shown. Here we have the dashed line that is at 1 atmosphere, and here the solid small thin line is at 1 gigapascal. You can see again how the boundaries are moving with increasing pressure conditions. We consider the crystallization of magma A in a large magma chamber at 30 kilometers depth. That means we are talking about a pressure of 1 gigapascal below the crust. As this magma cools under equilibrium condition, the magma will evolve along the path A, B, C, D. At 1 gigapascal we will start here, A to B, to B to C, and C to D. So, and here we have now this plot. Again, here the magma chamber, and in the contact zone to the surrounding country rocks, we are forming a chill margin as it is shown here. That is again the chill margin here at the country rocks. So then we are forming at first a forsterite dunite layer. Yeah, that is the forsterite dunite layer. So, and then we are going from A to B. Here we are in the forsterite plus liquid. We are removing the forsterite, the liquid is left. Then we are going along past B to C. We are forming here a forsterite enstatite layer. This is an Harzburgite, yeah, that is this layer here. So then we are going to from C to D. Then we are forming a spinel enstatite layer, that is here. So, and finally here, we are having then here at point D, we are forming a rock which contains anortite spinel plus enstatite, that is a spinel norite layer, which is a gabbro. That is formed here, yeah? So, and that is then easier to understand when you are looking at this in such a triangle, and here we have then a melt left in the center, yeah? I think that is now more clear than before. So here we have something else, we have repetitive layers. So we have here again diagram A, diagram B. On the diagram A we have a part of the triangle anortite, forsterite, and here on this side we have then here the silica as it is shown here, yes, that is this. Here we have the spinel plus the liquid, the forsterite plus the liquid, the enstatite plus the liquid. So, but now we are crossing here always the boundary between the enstatite and the forsterite. Why is this? This diagram shows how competitive nucleation and growth rate of olivine versus enstatite force the evolving melt to crisscross the forsterite enstatite liquid boundary repeatedly. So, and this is then shown in diagram B. This diagram shows such a back and forth movement of the evolving melts result in the repetitive development of alternate layers of dunite and olivine and orthopyroxenite, yeah? Here we have always this olivine, orthopyroxene, olivine, orthopyroxene, olivine, orthopyroxene, olivine, orthopyroxene, olivine, orthopyroxene, yeah? And that is when we have always this crisscross. So, and that can be variation downwards, upwards in temperature, for example, yeah? Or when we have just an influx from outside, maybe from another melt. So we need a process which always leads to this crisscrossing to the forsterite enstatite boundary, and then we can observe this in the rock sample. Then we'll form then such repetitive layers of olivine enstatite, olivine enstatite, olivine enstatite. Okay, that should also be clear. So now we have here again such a magma chamber A and B. So, and here we have two situations. We have here at the top, we have again the crystal melt mash. At the bottom we have the crystal melt mash, and then we have a suspension zone, and between we have the melt, and here we have a convection cell. That is then a convection in a magma chamber, and here we are forming solid rock at the top and solid rock at the surface. So, and here we have a density current. We are forming also the crystal mass at the top, the crystal mass at the melt, and then we have sinking of crystal plus melt cluster, like it is shown here. That is just due to density, and then it sinks down. and becomes spreaded across the bottom, yeah? So what is written below? A schematic diagram depicting how roof crystallization gives rise to crystal melt mush. Chunks of such a mush fall off owing to its greater density than the underlying melt. Crystals from such a mushy material settle down on the floor while compaction due to accumulation of the crystals and pressure of the overlying melt. Due to the accumulation of the crystals and pressure of the overlying melt, squeezes out the interstitial melt from the mush, and such melt moves upward and mixes with the overlying melt. Such movements are essentially localized convection currents, and that we have here, yeah? So here we have, due to the weight, we are squeezing the interstitial melt out, and then it goes, mixes up with the melt above. So what do we have here? We have a sketch of a photomicrograph showing a quartz xenocrystal, that is the quartz xenocrystal, surrounded by orthopyroxene needles, that is here in a tolleiite basalt with a magnification of 160. Yeah? So that is now nothing special. We have the quartz xenocrystal, and the quartz xenocrystal has picked up from the melt, and afterwards we have the formation of orthopyroxene needles in this tolleiite basalt. So here we have now the relationship between assimilation, crystallization, and the delta T, which means that is the temperature difference between 0 and 200 here seen on the x-axis, and here we have the melt relationship, that is melt, and that is the crystallization. So and when we are and here we are going down with the temperature. So and here the curve rises up. So because with decreasing temperature, we are forming more crystals out of our melt, yeah? Yep. So now this is also a very nice picture. We have here a channel, yeah? That is a channel, and that is again this rubbish. That is a channel. So, and I mean, if magma flows through a channel, then at the top and at the bottom, not only at the top and at the bottom, you know, that is like a tube, but it will start to crystallize from inside to outside. So, and then the velocity at close to the surrounding rock units becomes smaller, yeah, because there the magma cools down, then it becomes more stiff, and the speed in the channel is then higher, yeah. So that is the flow velocity is at the rim smaller, yeah, because then crystallization takes place at the rim. Our channel becomes from time to time more and more thin till it becomes stacked. So, and here we have then such a sill. It becomes then, as I told you, it becomes then smaller and smaller, and then it becomes stacked, yeah? So we have the flowage differentiation in a dike, yeah? Magma flows through the dike, focuses the suspended crystal to be concentrated in the center of the dike, yeah? And at the rim it crystallizes, it will cool down very fast, and then it becomes more and more solid. And therefore we have in the center a higher flow rate compared to the rim. So, and here we have another photomicrograph of a pigeonate rim around an orgite crystals in a Rio Grande basalt. So an orgite, you know, that is a clinopyroxene, and the pigeonite, that is a calcium-rich orthopyroxene, has a little bit more than 5% calcium inside, and that formed at high temperature conditions. So in a very, very fine-grained matrix, yeah? So, and here we have now another diagram showing us the chemical variation, yeah, from such a small sill, yeah. Here we have scale 1 millimeter, you know, that is not too big, yeah. 1 millimeter is this, so and there we have, at the diagram at the bottom, we have here the isotopes, strontium isotopes, and that is the microns from the rim. We have here the rim, here we have the rim, yeah, here we have the rims, yeah. And here we have the center, yeah, the core. Can you see this? Yeah. So here they have measured through, here they have measured through. And that is, these are the traverses, that is SS23A TR1, that is this one. And then we have SS23A TR2, that is this one, yeah. So in there they have measured through this plagioclase crystal, the zonation through this plagioclase crystal from rim to the core and again to the rim. So what is written here, strontium 87 to strontium 86 zoning in a plagioclase crystal from a decantrap lava. The top two panels show cathodoluminescence images of two giant plagioclase crystals. Yeah, two giant plagioclase crystals. Yeah, they are quite big. Yeah, they are more than a centimeter long, maybe 1.5 centimeters, something like this. Yeah. The white dotted line shows the tracks along which 87 strontium to 86 strontium ratio was determined. The bottom panel shows 87 strontium, 86 strontium zoning in two crystals. Ground mass plagioclase crystals is shown as red squares. On the y-axis on the left. Ah yeah, this is this. So, but here you can see how the zonation changing chemically, yeah, from here at the core of both crystals, we have much lower values in strontium isotopes like at the rims, yeah, because our crystal is growing from core to the rim and not from rim to the core, yeah. So, and that helps us to identify then the geological history or the story behind every mineral which we are collecting in our, or which we can analyze from our rocks. So here we have this diagram, the system firelight, lewisite, silica, showing two liquid immiscibility fields. So here we have this liquid immiscibility field, here we have the next one. So the one in the middle is more relevant to late stage immiscibility in basaltic magmas. The dashed lines are tire lines that connected the conjugate liquids. LC is Lewisite, OR is autoclast, TR is tridymite, CR is cristobalite, and FA is firelite. So, and you know by now what a immiscibility field is that we have here. Such composition does not exist in nature, yeah? So what do we have here? We have here again at the top a diopside anorthite forsterite triangle. We have here the different pressures, 2 gigapascal and at 1 atmosphere. And we have here the cooling path A to B to D. So and now we have here along this cooling path in B and C, we have here the oxides in weight percent, calcium oxide, magnesium oxide, aluminium oxide. Yeah, here we have this black dots inside, white dots inside, and white squares inside. Here from A to B, olivine fractionation will take place. Yeah, here we have the olivine. Here we are going from A to B. We have here forsterite plus liquid. We are going from here to here. From B to D, we have then olivine plus plagioclase fractionation, and that is from here to here, and that is seen in this line. And of course, when we are going from B to D, we have also an increase in aluminium oxide because we are forming anorthite here. So, and that is F, that is our liquid fraction. Here we have a lot of liquid going here from 1.0 down to 0.5. So, and here we are forming more and more crystals out of our melt. So here we have the next one, that is again the liquid fraction. Here we have the calcium oxide versus aluminium oxide. We have here the troctolite fraction, that is, you know what a troctolite is, we have discussed it when I showed you the gabbro triangle, and here we have the olivine gabbro fraction, and that is strongly called because here we have then forming an olivine gabbro. That means we are having here more magnesium inside. The melt becomes then, the liquid fraction becomes then more depleted in magnesium and more enriched in because it becomes more depleted in magnesium because the magnesium goes into the olivine. Here we have again a FMG diagram, that is magnesium divided by magnesium plus iron, and we have the oxide weight percentages, yeah. We have here olivine, and then we have here the olivine accumulation. While we are going down, we are increasing the Al2O3 in our melt because it becomes relatively enriched. So, and when we have also an enrichment in CO2, which becomes depleted afterwards because we are forming then the anorthite. So we have now a selected composition diagram. So what is written here, A to D, selected composition of lavas from the Kilauea shield volcano, Hawaii, are plotted to illustrate olivine accumulation and fractionation of olivine, plagioclase, and orchite at different stages of the evolution of Kilauea volcano. B to D illustrate how different mineral fractions have shaped the Kilauea liquid line of descent. E is a summary of the entire trend. So at first we have here the XMG, or here a high XMG, here and low. So it becomes then always lower because from here to here the XMG becomes lower because we are removing more and more olivine out of the melt. Then we are starting to remove olivine and CPX out of the melt, yeah. So and here we have plotted it against CaO on the y-axis, and when we are starting to form the plagioclase, then the concentration of CaO in our melt becomes also lower because the plagioclase takes a lot of CPX outside. The plagioclase takes a lot of calcium oxide out. So, and I mean the CPX as well, but there we have still a small increase in CPX because it's all relative. But then when we are forming additionally the plagioclase, then the calcium oxide concentration goes massively down in our melt. So here the same, we have here olivine crystallization, yeah, our XMG goes down. Relative to that, our other oxide weight percentage goes up, yeah. So from B to C, we have then a crystallization of olivine and of CPX, yeah. So our XMG goes down. So, and here from C to D, we are starting then to crystallize olivine, plagioclase, and CPX, and then we are removing also calcium oxide out of the melt and magnesium oxide out of the melt. And here we are starting then also to deplete our residual melt more and more in Al2O3 because we are also removing then the aluminium from our melt. I hope that is now also clear. Here we have some other fractionation trends. Percent A versus percent B. So we have A, that is a monomineral, deals with a monomineralic fraction. So we have only one mineral inside. So we have here mineral M, we have a parental magma 1. So and then we are removing one mineral, a monomineralic thing. We are monomineralic, that means we are removing out from a melt just one mineral. That could be an olivine or a pyroxene or a plagioclase, yeah? So then we have a straightforward fractionation trend. So shown in this arrow at figure A, that is this one. So now we have a two-phase cotectic fractionation, also isobaric or polybaric. Then we have here the mineral M. We have here parental magma 2. And here we have the fractionation trend. And here, for example, we have a two-phase Cotectic fractionation, polybaric, not isobaric. So, and then we have here a parental, the trend of the parental magma 3. And here we have the mineral fractionation trend. So, and then they are chemically totally different. Here we have the fractionation trend of the parent magma. Here we have the mineral. It is all on one trend for the monomineralic fraction. Two-phase cotectic fractionation. Here we have the development of the magma. So, and here we have the development of our mineral. So, and here we have a polybaric two-phase cotectic fractionation. Here we have the trend of our parental magma, and here we have the trend of our mineral with decreasing temperature, with decreasing pressure. So here we have some other diagrams, the nickel distribution and the strontium distribution in ppm. So strontium and nickel variation in evolving magma. F is the residual melt fraction that we have here, yeah, at the x-axis. EC is the equilibrium crystallization. FC is the fractional crystallization. Partition coefficient used for SR, anortite in liquid 2.5, diopside in liquid 0.1, olivine in liquid 0.005. So here we have then the nickel, and you know the nickel is a compatible element, becomes also removed, becomes also taken away very early from the melt, and nickel is enriched in the olivine. So our fraction, the nickel concentration decreases here dramatically, where we are forming olivine, where we are forming a lot of olivine. So it goes down when we have a mixture of olivine and anortite, and then more down when we have a mixture of olivine, anortite and diopside, because the anortite and the diopside does not take the nickel into the crystal lattice, but the olivine does. The same for the strontium. We have high strontium values when we are talking about olivine, anortite and diopside, because the strontium is located then in the crystal lattice from the anortite. Or in the field where we are talking about olivine and anortite, then we have there also a lot of strontium inside. So, but when we are going to the last field on the right hand, we have only olivine, and then the strontium distribution goes rapidly down, because the olivine does not take the strontium into the crystal lattice. So what do we have here? Here we have two diagrams. That is a stratigraphy of the Deccan Trap lavas. Lava flows from Western Ghats. Yeah, the Deccan Trap, that is a continental flat basalt, and on the right hand we have a neodymium strontium isotope composition diagram of Deccan Trap basalts from the Western Ghats area, and then you can see how they are chemically, what they are showing chemically for variation. So we have here on the block diagram on A, we have the subgroup VAWAI. So we have here the Desur, the Panala, the Mahabalesavar, the Ambenali and the Pollard Boer. Then we have the subgroup Lonavala with the Boucher and the Kandala. And we have the subgroup Kal Subai with B. Maskankar, Tankurvadi, Neral, Igapuri and Jawar. So, and then you can see already how different they are. So here we are sitting in the subgroup Lanu-Valu, with the Boucher has very high strontium isotopic values. Here we have the Kandala, that depends also to the subgroup of the bush of the Lonavala. Has lower but still high strontium values and tends also to have high epsilon neodymium values. Then you have here the Java Igapuri. This belongs then to the Kal Subai subgroup. And here we have the Ambenali and the Manabaleshwar having lower strontium, but here the Ambenali higher epsilon neodymium, and they are belonging to the subgroup of the Y. So when we are using these geochemical fingerprints, here the isotopes, we can differ all the different rock types from each other, and we can reconstruct the formation history, for example, in this example, for the Deccan Trap basalts or for the Deccan Trap lava flows. So then we have here an assimilation, fractional crystallization of magma. Here we have lanthan on the y-axis, and lanthan, that is, as far as you know, lanthan, that is a light earth element, yeah, very on the left hand of the incompatible elements versus the strontium isotopic ratios. So, and when the lanthan values rises up, then that is a sign. When the lanthan and the strontium isotope values rising up, then it is a sign for the contamination of the magma with some other rock types due to assimilation, yeah? So, and then we have the contamination, for example, from a source outside, yeah? That means, when your magma rises up, then it is in contact with the country rocks. So, and then contamination processes starting, that means pieces of the wall rocks falling inside in your magma, and then these pieces of the wall rocks in the magma will become molten up, and then it will change the chemical composition of your original magma, and therefore we are talking about contamination, for example. And here the author used this relationship, lanthan versus strontium isotopes, and to identify if contamination has taken place in your investigated basaltic rock sample. So here we are coming again to Bowen's reaction series, yeah. We have, or I told you about Bowen's reaction series also in our first chapter of igneous petrology. Now we have here a more detailed chapter of igneous petrology with 3 inset diagrams below. So when we are talking about Bowen's reaction series, we have a discontinuous series and we have a continuous series. At the discontinuous series, we are going from olivine over we are starting to crystallize olivine, then pyroxene, then amphibole, then biotite, and at the end, a potassium feldspar muscovite quartz. So when we are looking at the pyroxenes, we are going from hypersteam to orgite. When we are looking at the continuous series, we are going from the calcium-rich plagioclase to a sodium-rich plagioclase, ending up with a potassium-rich feldspar, muscovite, and quartz as well. So then we have here, very on the left hand, we have at first the basaltic parental magma, and then due to fractionation and crystallization, we are forming from our basaltic parental magma an andesitic magma, because the chemistry, the bulk chemistry of our melt will always change, because we have always fractionation, differentiation, and crystallization processes inside. We are removing crystals from our melt, and they will sink down to the chamber to the bottom of the chamber. Others will floating up at the top of the chamber, and therefore the residual melt will always change their chemical composition, starting then with a basalt as a parental magma, will go over an andesitic magma, and finally we will get a rhyolitic magma, which is felsic, yes. So at these three insets below, we have at first the basaltic magma with a chill margin at the rim, to the contact rocks. So basalt magma in place in a crustal magma chamber. So then we have a fractionation and crystallization takes place. Then we have here in the inset in the middle, we have olivine, pyroxene, and calcium-rich plagioclase fractionate out, leaving an andesitic magma in the center. Yeah, we are going here. Here we have our basalt magma. Yeah. So then we are making here olivine, pyroxene, and calcium-rich plagioclase will fractionate out. Then we have here inside the andesitic magma, which is here. Yeah. So now we are continuing with fractional and crystallization process. So, and then we have here at the end this situation. Then we have amphibole, biotite, and more alkali plagioclase fractionate out to leave a rhyolitic liquid in the center that we have then here. Yeah, that is this one here in the middle. So that should be clear, and that is now a summary actually from all these diagrams which I showed you before. Yeah, how it depends on the pressure, how it depends on the temperature, how crystallization processes depends on the volatile concentration, if we are talking about a high volatile concentration, if we are talking about a lower volatile concentration, and. That is all this stuff, yeah? Going back to the AFM diagram here at the top, we have then the crystallization trend from the scare guard intrusion, and we are forming two immiscible liquids out of it. We have one area where we have forming more iron-rich rocks, and the other one where we are forming more sodium and potassium-rich rocks. And here below, we have then, for example, again the common toleitic trend, yeah? So here we have a nice picture from the Bushveld complex, and the Bushveld complex is a layered intrusion, and here these dark bands, these are layers of chromite separated by plagioclase, yeah? So, and chromite is a mineral which is formed at very high temperatures, and it becomes then removed very early in our magma, in our crystallization sequence, will sink to the bottom of the chamber, and there it will become enriched and forming then these bands of chromite, where they are mining it now finally in the Bushveld intrusion in South Africa. And I mean, here we have the layers of chromite separated by plagioclase. And the dark layers are the chromite, and the white layers, these are the plagioclases, yeah? So here we have another microphotograph, and the micrograph of an unusual is from an unusual mantle xenolite from Oahu, Hawaii, showing layered structure. The colored minerals are almost all olivine, and the opaque mineral is a chromite spinel. So that is the relationship here. The picture was taken with polar crossed and gypsum plate inserted. The pink mineral intercobulus with high relief is a garnet. Garnet is isotropic and therefore shows the same color as that of the gypsum plate. So, and the gypsum plate shows these high interference colors. Here we have another map here on diagram A. That is the map of the Skaergaard intrusion, yeah, MBS. MBS, that is the marginal border series. UBS is the upper border series. Where is UBS? Yeah, that is this one here. That is the UBS series, yeah, that is here. And here we have the MBS is the marginal border series. The layered series is composed of the, of the lower zone, the middle zone, and the upper zone. And BS is the basis stoppen sheet, yeah? So, and here in B we have an east-west cross-section of the Skaergaard intrusion. So we have here again the UBS, that is the upper border series. Then we have here the BS, which is the basis stoppen sheet. Here we have the upper zone. Here we have the middle zone, the lower zone, and here we have a hidden zone, and that is the MBS, and that is the marginal border zone where this hot melt from the intrusion itself got in contact with the surrounding country rocks. So, and that is then a layered intrusion. We have here a sandwich horizon. That is the depth and we are talking about a depth of 2,500 meters. We have here a layered series. We have the upper zone, the lower zone in the middle. There we have the lower zone. Then here we have the chemical composition in forsterite. Here we have a forsterite 68, 56, 48, 40. So it becomes then more and more iron rich from the lower zone to the upper zone. Yeah. So the same chemical variation we can see in plagioclase. We are starting with an anortite 66 going down with an anortite to an anortite 25. So that means from the lower zone to the upper zone, our plagioclases becoming always more rich in sodium. From the lower zone to the upper zone, they are becoming then more rich in sodium. So we have at the lower zone a more anortite-rich plagioclase. At the upper zone we have a more sodium-rich plagioclase. Yeah. So then we have here the pyroxene. We have here an inverted pigeonite, that is this calcium-rich orthopyroxene. Then we have here the calcium-rich clinopyroxene. We have here ilmenite in the middle zone, magnetite, apatite, and granophyre. Yeah. So and here we have this layered intrusion, and here in the Skaergaard intrusion we can observe a cryptic layering in the layered series of the Skaergaard intrusion. And here on this diagram we can also see the chemical variation of our diagram of our minerals inside. Yeah. So here we have another temperature pressure diagram. So from crystal mush here at the bottom, and from a molten rock above. So the left panel shows the delta T over delta P slope of the magma crystallization liquidus curve may intersect the magma adiabat, the magma temperature in a large intrusion. This will cause early start of crystallization and longer crystallization for the bottom part of the intrusion. So here we have this boundary between melt, and here we have the crystallization. We are going down with here we are going up with the pressure. Here we are going down with the here we are going from the left to the right up with the temperature, and here we are going down with the pressure from the top to the bottom. So and then we have here, just in this area, we have here melt. We have here the temperature of the magma, yes. So and at the lower part, when we have less pressure, then crystallization will take place. So and this crystallization, these crystals will then become settled at the bottom of our magma chamber. Yeah, should also be clear. So here we have now another picture from the Bushveld intrusion. Here again, where the Bushveld intrusion is. Here we have Pretoria. Here we have South Africa, Botswana, and here we have Namibia. Here we have a map showing the location. That was this what I have shown you, and the distribution of the Bushveld intrusion. That is this is this part here, yeah, and that is this part here. So and here we can separate it in an upper part, in a main part, in a critical part, a lower part, and the marginal part. And these are the zones of the Bushveld complex. So in the upper zone, which is 1.5 kilometers thick, we have a ferrogabbro and a ferrogranophyre. Then we have the main zone, which is formed by lithologically, which is formed by a gabbro and an anorthosite. Then we have the critical zone, that is the Merensky reef. We have then anorthosite, norite, feldspathoitic, pyroxenites, orthopyroxenites, and the chromite layer. And we have the lower zone. We have mostly orthopyroxenites, feldspathic and feldspathic orthopyroxenites. And then we have a marginal zone. We have here a xenolite bearing norite. So now we have here the next diagram, the appearance of the cumulus phases. Here we have the change in chemistry from the olivine forsterite 0 to forsterite 48, and we have an olivine gap. Within these olivine gaps we are separating also the magnetite and the chromite, and in the critical zone and the lower zone we have forsterites with a forsterite component 86, 85, and then we have a very at the bottom olivines with a very high forsterite with a very high forsterite concentration inside as well, or forsterite component inside as well. So then we have the plagioclases, varying also extremely in their chemistry. From the upper zone we have plagioclases ranging from anortite 30 to anortite 53, going over to a plagioclase anortite 60 in the main zone. And in the critical zone we have a plagioclase with an anortite component of 76 to 80. So then we have the pidgeonite. Here we have in the main zone we have pidgeonite. So and in the critical zone and in the lower zone we have the orthopyroxenes, and these orthopyroxenes varying also in their XMG. So and then we have from the upper zone till to the boundary zone of the critical zone, we have here also the crystallization of augite. So now we have here the next diagram. Number A, we have here the triangle diagram, silica, forsterite, firelight. So, and here we have the crystallization trend of enstatite. From 1 to over 2 to 3, we have here olivine plus liquid. Then we have silica, this SiO2 polymorphs plus liquid. We have here a calcium pure pyroxene plus liquid. So in diagram number B, we have here the crystallization trends, the olivine composition line from total solid. So we have here the parent magma P, we have here F, the final liquid, and here we have diagram C, we have the fractional crystallization of P. And now we have to stop because the shit dog from the neighbor is always barking and disturbing me. Okay, then we will just continue within the next few days. Okay, and I will now load up this video and we will then just next time continue with this diagram, because now it is not possible with this barking always. Okay, see you then. Bye.